In this problem, we're given the pole zero plot of transfer function of a stable linear time invariant system. So this pole zero plot is given. We also know that the transfer function is a rational function of S. And what we need to find is h of t, the impulse response to within a scaling factor. And this h of t is the inverse Laplace transform of h of s. And the first step is to find h of s. Because h of s is a rational function of s from these poles and zeros, we can actually write the expression for h of s2 within a scaling factor. So to do that, for each zero in this graph, we'll have a term in the numerator of h of s. Since there is a zero at s equals 0, we'll have the term s in the numerator. For the zero at 1 plus 1.5j, we'll have this term in the numerator. For the other zero at 1 minus 1.5j, we'll have this term in the numerator. Then there is a pole at s equals -2, because of which we'll get this factor s plus 2 in the denominator. And there is a pole of third order at s equals 1. So we get a third order factor in the denominator corresponding to this pole, which is here. So that is the first step. And then to make our algebra simpler later, what we're also going to do is simplify this expression if we can. So what we see is that in the numerator, we have two factors associated with complex conjugate zeros. It's easier if we combine those two factors into one. And we can do that by considering this formula, a minus b times a plus b. So if we call this s minus 1a and 1.5j b, then we can see that it's in this form, a minus b, a plus b, which is a squared minus b squared, right? So this whole thing is a squared and we have b squared. And once we do that, expanding this numerator, we get to this h of s. So we have our h of s, and the second step is to find the partial fraction expansion for h of s, because our goal, eventually what we'd like to do is find the inverse Laplace transform of h of s. And for that, we'd like to find the partial fraction expansion first, because if we do that, we'll be able to find the inverse Laplace transform for each term in the expression for h of s. So we'll let h of s equals this. We have k1 divided by s plus 2. This is because of this term, this factor s plus 2 in the denominator. And because we have a third order pole, a third order factor in the denominator, we'll have three ratios or fractions corresponding to that. One with power as high as the actual power of that factor, which is 3, and then decreasing powers. So we have 3 and then 2 and then 1. So we go up to 1. So if we have 3 factors, repeated factors, then we have 3 fractions associated with that factor in the partial fraction expansion of h of s. So all 3 correspond to s minus 1 cubed. Then we have to find the values for the coefficients, k1, k2, k3, and k4. Finding k1 is straightforward. What we have to do is take the expression for h of s, multiply that by the factor associated with k1, which is s plus 2, and then plug in s equals -2. -2 because it is the pole associated with k1, or the factor s plus 2. So this is the expression h of s times s plus 2. We plug in s equals -2 and we get 5/6 as the value for k1. And finding the value for k2 is similar. we start with h of s, multiply that by the factor associated with k2, which is s minus 1 cubed, and then we evaluate the result at s equals 1 because that is where the pole associated with the factor s minus 1 is. So we plug in s equals 1 and we get the value for k2, and it is 3/4. Now to find k3 and k4, we'll have more steps. To find k3, we'll need to differentiate this term. Finding k2 was simpler. We just had to consider this function and plug in s equals 1. To find k3, before we plug in s equals 1, we have to differentiate this term with respect to s once. To find k4, we would have to differentiate this term with respect to s twice. Okay, so let's see how we do that. For k3, again, we take h of s multiplied by s minus 1 cubed. Although the factor associated with k3 is only s minus 1 squared, we still have to multiply by the maximum power of s minus 1, which is 3. And then we differentiate this with respect to s, and we also have a factorial in the denominator. This equals the order of the derivative. This is the first order derivative, so we have 1 factorial. When we have second order derivative, we'll have 2 factorial. Third order derivative, 3 factorial, and so on. Okay, so the expression for this is over here. Now we differentiate with respect to s using quotient rule, and we get this expression for the derivative, and we plug in s equals 1, we get the value for k3, turns out to be 1/2. Okay, now k4. For k4, again, we start with this term, but we have to differentiate with respect to s twice. And then since the order of the derivative is 2, we divide by 2 factorial. Differentiating this twice means taking the first derivative, which is, we already have that, right? And then differentiate the first order derivative again with respect to s. So first, let's copy the first order derivative over here. This is the first order derivative. And then if we differentiate with respect to s one more time, we'll have the second order derivative, which is exactly what we're doing here. So this is what we get using quotient rule for derivative again. And we plug in s equals 1 in this long expression, we'll get the value for k4, 1/6. Once we have all these coefficients, we can write our h of s in this partial fraction expansion form. The next step is to find the inverse of each fraction. To find the inverse, we also need to know the ROC associated with each term. And the original pole zero plot given to us was this. And we're also told that the system is stable. So first of all, we have to find the ROC of the overall h of s. If the system is stable, then we have only one choice for the ROC of h of s. We cannot consider this ROC to the left of the negative 2 pole, because that would not include the imaginary axis. To make the system stable, we have to include the imaginary axis in the ROC. If we take this ROC, which is to the right of the pole at s equals 1, that would make our system causal, but it would be unstable because it wouldn't include the imaginary axis. So the only choice for ROC that we have is that would meet the constraint that the system is stable is this, the one between the pole at s equals -2 and the pole at s equals 1. And then we have to consider, try to find the inverse of each term in h of s. So the overall goal is to find the inverse of the whole function, the linear combination of these 4 functions. And using the linearity property of Laplace transform, what we can do is focus on one term at a time. Okay, so let's look at this pole. So the pole is at s equals -2, and the factor associated with that pole is 1 over s plus 2. And the inverse of such a ratio could be of the form, it could be of the form e to the -at u of t, or it could be of the form -e to the -at u of minus t. But if we pick the second option, that would make our function left-sided function. But looking at this ROC, we can tell that we have to pick the right-sided function. That means we have to pick this function, this option for 1 over s plus 2, because we need to have some overlap with the ROC of h of s. The ROC of this would not overlap with the ROC of h of s. The ROC of this does overlap with the ROC of h of s, so we consider the first option. So using that formula for the inverse of 1 over s plus 2, we get the inverse of this as e to the minus 2t u of t. And we also have this constant term 5 over 6. Using linearity, we can apply the same constant in time domain as well. If we have some constant in s domain, the same constant appears in the time domain. So that's the first term. Now let's consider this one. Again, a linear factor in the denominator. So the pole associated with that fraction is over here. And now again, for this term 1 over s minus 1, we have two possible choices. One would be e to the -at u of t, and one would be -e to the -at u of minus t. If we pick the first option, e to the -at u of t, this is the right-sided function, and the ROC associated with that would be to the right of the pole over here. And that would give, that would have no overlap with the ROC of h of s. So the first option is out. We have to pick the second option because the second one is left-sided. If we pick this option, its ROC is to the left of the pole, and that would have some overlap with the ROC of h of s. So we pick the second one. Let's erase the first one. So using this formula for 1 over s minus 1, we get the inverse Laplace transform of 1 over s minus 1 as -e to the a itself is -1, so we get e to the t u of minus t, and we also have the constant 1 by 6. So we found the inverse Laplace transforms for the two terms already. Now we have a square term and we have a cubic term as well. So how do we find the inverse of those? All right. So to find the inverse of a square term, we have to consider linear. We have to start with some reference function, and the reference function would be the corresponding linear term. And the linear term is this, 1 over s minus 1. So what we know about that 1 over s minus 1, we already know that 1 over s minus 1 is the Laplace transform of -et u of minus t (1 over s minus 1). So this is what we know, and the ROC is to the left of the pole at s equals 1. And now consider multiplication by t property of Laplace transform. If in time domain, we multiply our function by t, okay, so I'm multiplying the function by t in time domain, we know that in S domain, what we have to do is differentiate with respect to S. And we also have a negative sign. So negative d over ds is the operation in S domain if in time domain we are multiplying by t. So consider this derivative, 1 over s minus 1. The derivative of that would be negative 1 over s minus 1 squared. And we already have this negative sign over here, which cancels the other negative. And we get 1 over s minus 1 squared. So what we know is that the Laplace transform of negative t e to the t u of minus t is this. Okay, so this is the expression that we need to use. Okay, so this is the expression. The inverse of 1 over s minus 1 squared is this. So let's copy this over here where we have a square term. Okay. And in S domain, we also have a half. So we need to have that half in time domain as well. This half. Okay, now we have one more term left, which is 1 over s minus 1 cubed. Okay, so let's consider that. What we've already established is this. The Laplace transform of negative t e to the t u of minus t is given by that. Now we're going to apply multiplication by t property one more time. Okay, so now what we're going to do is multiply by t in time domain. That means I get a square in time domain. And then in S domain, I have to take negative d over ds of whatever function I have. And if I do this derivative, I have a negative sign. So I get negative 2 divided by s minus 1 cubed equals 2 by s minus 1 cubed. Okay, so what we can say is that negative t squared e to the t u of minus t has Laplace transform of 2 divided by s minus 1 cubed. If we divide both sides by 2, we get this in the time domain, and in the S domain, we can get rid of that 2. So we can use this as a formula. Now let's copy this. So because for 1 over s minus 1 cubed, the inverse Laplace transform is given by this. Okay, so let's copy that. Okay, so the inverse of this is given by that. And since we have 3/4 in the S domain, we need to have that 3/4 in the time domain as well. So we get negative 3t squared and 2 times 4 in the denominator, which will be 8. So what we have now done is we found the inverse Laplace transform for each term that we have for h of s in h of s. Now let's take all these, and using linearity property of Laplace transform, what we can say is that the overall inverse is this sum. Okay, so this is the answer.